Okay, guys, I'm really sorry about the confusion with the links. This is not the first time I'm doing this mistake, so at least I'm consistent. I hope that this is the last time I do this mistake. I really apologize, Ori. Just on a related note, I will post an invitation to the seminar of our friends in the chat in a few minutes. And now we are moving to the main part of our seminar. I'm going to present our current presenter, which is Ori Plonsky, in a second, and then we will proceed as following. The seminar will be for about 50 to 55 minutes you will have for your presentation, and then those in a few minutes for questions, and then those who have to go will go, and if it's fine with you, we will stay for about 20 more minutes to those who want to ask additional questions. So now eventually, again, I'm sorry for the confusion. I'm going to present our presenter, who is Ori Plonsky, who is a young, although I'm younger, and bright, unfortunately I cannot say this about myself, a bright scholar who has already published many papers in great top journals, including PNAS and Psych Review and whatnot. He is also the receiver of the Einhorn Young Investigator JDM Award, which is highly prestigious. So Ori, we have a thing or two to learn from you, and now I hope you will learn them from your presentation. And now the floor is all yours.
Great. Thanks very much, Efim, for this way too much kind introduction. So the title of the talk that was sent to you in all those links, it's actually longer than this, but I figured that it's too long. So basically, this talk is going to be about hybrid models for predicting decisions under risk and uncertainty. This is joint work with mainly with Ruth Appel, Ido Erev, and Moshe Ternholz. The first and last of these are data scientists, and I guess you know Ido, and maybe many of you know also Eyal. Okay, so let me start with a short motivation, because I know that many times when I'm talking about prediction, people don't always understand why it's very why it should be a main point. So let's say we want to incentivize desired behavior in the population. For example, let's say that we want to get people out of their cars and into public transportation, or into many people driving the same car and so on. And there are programs around the world, and there's supposed to be a program in Israel as well that the country pays people for not driving, for leaving their cars at home. And if we want to implement such a policy, and we have some budget for it, then we want to exploit this budget in the best possible way. So we turn to behavioral scientists, behavioral economists, and ask, what is the best way to incentivize a specific behavior like this, given this budget? So maybe a behavioral economist A says, well, we know the loss aversion is important, then we should give them money at the beginning of the month and then take away every time they take their car. Another one says, well, prospect theory and so on tells us there's overweighting of rare events, so we should use lotteries, give them some large amount in small probability every time they leave their car at home, and so on. And there are many such effects that can be implemented. So basically, we have a lot of possible treatments, a lot of ways to use this budget to incentivize the desired behavior. One way to check which one is best is to experiment, see what's best. Well, we do some sort of a pilot or an experiment with many treatments, and then we see what works best. And recently, there have been several papers. One of them here by Milkman, Katie Milkman and her colleagues, discussing mega studies in which basically they run many different treatments in parallel to see what works best to motivate a specific behavior. And this is from their paper, from that paper of from Nature. This is for incentivizing people to going to the gym. Each row here that you see is one treatment, and this is just the first 30 treatments. They had 54 different treatments, and this is sorted by rank order. So this is the best treatment here, and this is some sort of a baseline. And what you see here is the result of each of these conditions, and you can see that this is the best treatment, and a comparison of all the treatments brings us to some realization that maybe this is the best one, or the first few are the best ones, given the budget to implement such a policy. Now, the problem here, well, that's great. If you can do it, that's great. I support it. I think it's a great paper. I think it's a great way of doing things. And if you haven't read that paper, I encourage you to do it. It's very interesting. But one problem is you might not have the possibility to run 50 or 100 different treatments to find the best one. Another is what happens if then the government decides, well, that we have a change of budget. Now it's not the original budget that we planned. So all the treatments that you actually planned and piloted on, they're invalid, right? Because there's something else going on. So what basically we need to do here is we need to predict the behavior of the population given each possible incentive mechanism that we can come up with. So we ask, what is the incentive mechanism that will be most effective? Basically, given an incentive mechanism, predict the population response. So how can we do this? How can we predict behavior? One way is to ask behavioral scientists, what works best? Now, let's go back to the same paper. What you see here in orange is basically the predictions of experts, of behavioral scientists, of what works in each of these, how each of these conditions will work in practice. So you can see a couple of things. First, that behavioral scientists, these experts, wildly overestimate the effectiveness of each treatment. Second, there's basically zero correlation between what these experts predict would work best and what actually works best. So maybe behavioral scientists, at least for this specific task, very difficult task, prediction task, they're not very effective. So what can we do? Maybe we should go to data scientists. Data scientists do this for a living. This is what they do. They try to predict things. So maybe we should ask them what works best. So we have a prediction task. We think we can go to data scientists and ask them. What they do is they build predictive models. The models take as input an incentive mechanism, or the input of what we are trying to predict, and then returns some sort of prediction. By the way, this solves the change of budget problem, because the model doesn't care what incentive mechanism you put into it. It will spit out a prediction. The problem here is that usually there's too little data for training predictive models that data scientists usually do build. Because if we think of these policy problems, maybe we can run an experiment with 20, 30, 50 different treatments, but that's basically all the data we have, and data scientists, machine learning, and so on, they can't really make much good use to such small data. So what can we do still? So our goal is to develop a predictive model of choice behavior with relatively little data. Go to data scientists, go to behavioral scientists. Of course, by the title of my talk, it's clear that I support both. So I think that we can think of hybrid models that integrate behavioral ideas or theories into machine learning systems, algorithms. To give you a quick realization of what I'm suggesting is let's start by looking at this very, very simplistic idea of how data looks like. What we have here is a black box that we'll call nature. And our data is composed of variables, features, or predictors that we call X. They go into this black box, and then something happens and they return a response, some action, some outcome in the wild. somehow inside this black box, nature associates X and Y together. This is a very simplistic depiction of data. It goes back to Leo Breiman, a very famous statistician. Now, a prediction task is to find the function f such that, given the features x, the predictor variables x, f of x will approximate y to the best possible extent. And machine learning algorithms are very, very good at this, often. What's missing? Well, what is x? And I think that behavioral scientists, when the outcomes are behaviors, behavioral scientists are often very good at thinking of the stuff that nature that are inside the black box that is our behavior that makes us tick, right? This impacts this outcome, this impacts this outcome. We write a lot of papers saying this has an effect, this has an effect, this is an effect. These are all X's. So what I'm suggesting basically is to build hybrid models in which behavioral scientists develop theory-grounded features, and these are put in machine learning systems integrated together. Right, so before I show you some results, let me make a distinction of a couple of ways by which behavioral features can be thought of. Behavioral features can be very simplistic, and I call these behavioral insights, and they can be more complex, and I call these behavioral foresights. Let me make this distinction now. So behavioral insights, I think of these as specific behavioral phenomena that have a directional prediction of what should happen. For example, loss aversion is a behavioral insight. We know that losses, I'm sorry, Eldad, we know that losses loom larger than gains. So if losses are there, we should expect there is a directional prediction of how this should impact behavior. So this is a directional prediction. It's not specific to the data that we have. It's not fitted to the exact data. It's a general phenomenon, and this is something that we can use inside machine learning. More complex features are foresights, in which the behavioral scientist not only says, well, this phenomenon happens, and so on, but they also build a full model of how all these phenomena work together, the interaction of all these phenomena. And this gives a quantitative point prediction of what's going to happen in practice. This is usually fitted to the training data. And one example is cumulative prospect theory. So we have loss aversion, we have diminishing sensitivity to payoffs, we have overweighting of rare events. Everything is supposed to interact together. Cumulative prospect theory gives us a quantitative prediction of how they work together for a given context. So the quantitative predictions of cumulative prospect theory would be foresights. The directional predictions of the behavioral phenomena that are integrated in prospect theory would be behavioral insights. And each of these can be integrated into machine learning algorithms. Now, if we think that we can build models for predictive models of behavior, we can ask what level of theory integration do we need? And I think it can roughly be stored on a continuum. On one end of the continuum, nothing. We have deep learning, we have, I don't know, ChatGPT, GPT-4, whatever, and theory is useless under this assumption. Deep learning is king. We don't need any type of behavioral features, and all we need is more and more and more data, and that way we can predict very well. We can integrate a little bit of data, a little bit of theory into the models by integrating behavioral insights. And again, insights are the qualitative factors, the directional predictions of what drives behavior. And these are qualitative factors that are integrated as features, making the machine learning algorithm an integrator. It says how everything operates together. This is important, this is important, this is important, okay. And I think the data tells me that all these things function together in the following manner. Increasing the theory integration, we can also add foresights, in which we actually give as features the quantitative predictions of behavioral models. And then we can think of the machine learning algorithms as error minimizers. The behavioral model gives a prediction, but it's not very, very good. it's okay. And then the machine learning learns from the data how to correct for this prediction to make it to make the model more accurate. Finally, of course, we can say, well, we don't need any kind of machine learning or data-driven methods. What we need is full theoretical models that would be very good predictive models. Let me just mention that both elements in the middle are hybrid models. One end is purely machine learning, the other end is purely behavioral. In the middle are hybrid models. And I'm gonna discuss several examples of each of these models and how they do in the data that we're going to talk about today. So let me just briefly say how the paradigm that we're trying to predict behavior in looks like. So what we have is a binary choice between lotteries or between prospects, the most basic decision-making task out there. Mostly the choice is under risk. Sometimes it's under ambiguity, so it's a bit more complex than many of the normal stuff. We can have up to 10 outcomes in each of the two prospects, and this is how it looks like for participants. So we have, please choose between A and B. For example, one of the problems is A, 3 with certainty, B, 4 with probability 0.8, and then we have 270 different problems of that sort. So this is just one of 270 different problems. Most of them are randomly selected from a large space of problems. In some of the, well, most of the talk today, I will discuss a paradigm in which people choose, decision makers choose between these two prospects repeatedly for 25 times, both with and without feedback. And this happens as follows. In the first 5 trials, let's say that I'm a participant asked this question and I have to answer. So I click A here and it says you selected A. So there's no feedback and I do this 5 times in a row. Then starting trial 6, if I choose A, there's feedback. It says you selected A and your path is 3. Had you selected B, your path would have been 4. So there's full feedback explaining what giving the decision makers knowledge of the outcomes in practice. We have about 1,000 participants and 700,000 choices, and I will discuss other data sets that we analyze a bit later. Okay, before I'll talk about the models themselves, I want to talk a minute about model evaluation. Models in our game should predict new treatments. So I need to know for each incentive mechanism how the population will respond. A new treatment that I haven't seen in the data. So to do this, the best way is to take our data, our available data, the experiment, and then split it to train and test sets. The models see only the trained data. They only see treatments from the trained data. And the trained models that only get to see the trained data are evaluated only based on their ability to predict the held out test data. So the treatments that the models have never seen before. This is very common in computer science, machine learning, competitions, and so on. But note that model development must be, in order for the evaluation of the model to be robust and accurate, the model development must be independent on the test of the test data. And often, unfortunately, this is not the case. Even in machine learning conferences, when you see papers describing results, very often, the model development is not independent on the test data. For example, because the same, the experimenter themselves, they do the split between train and test, and then they happen to know the test data beforehand, even if it's implicitly, even if it's not made intentionally. Also, many times we take existing data sets in which we already know how models were, how previous models performed in the test data, and we develop new models. Again, the test data is known at the time of model development, which is a problem. To solve this problem, machine learning community and other communities as well have offered to use centralized evaluation mechanisms, which is basically model competitions, in which only the trained data is published. The models are submitted to the organizers of the competitions, and then the organizers evaluate themselves all models of the hidden test data. So the test data is never revealed to any of the participants during model development. And I will discuss two competitions that Ido and I and several others have organized in this talk, and I will and then a few other data sets. So in the choice prediction competitions, we have prediction tasks given a new choice problem of decisions under risk and uncertainty. We ask that you predict the distribution of aggregate choice. For example, like the pay for not arriving problem. The way this is done, we collect part of the data, some choice problems. We propose baseline models. This is what we think will work best. We invite other researchers to submit competing models. Then we collect the other part of the new data, which is new choice problems. And we evaluate their predictive accuracy based on their ability to predict in these new problems. So the first competition is CPC 15, 2015. And let's see what we got for theory integration within each of the models. So first of all, let me tell you that we got submissions without any theory, we got submissions without any machine learning, and we also got submissions of hybrid models that integrated insights, behavioral insights. Now the results, the best submission here without any theory was very poor, was ranked very poor. It predicted poorly. So machine learning without theory, at least for this data, worked poorly. The hybrid models were not statistically worse than the winner. The best hybrid model was not worse than the winner. And the winner was basically a purely behavioral model without any machine learning integrated in it, which is somewhat surprising because this is a predictive model competition. How is it that machine learning does not work? So what we did is we made a follow-up analysis in which we try to see maybe the submissions that we got of machine learning were poor, and then maybe we can do better. So what we did is we tried to look at different types of features, for example, insights, foresights, and non-behavioral features, and different types of algorithms, of machine learning algorithms, and we asked if we had participants using different types of features with different types of algorithms, submitting these models into the competition, how would they do? This is a follow-up analysis. So different types of features, for example, the first one is the objective features. This is non-behavioral models. What they do is just receive the raw data. Basically, this means that there's no theory whatsoever in these types of models. We can take it up a notch and say, well, we can add a little bit of behavioral theory by thinking of the naive way to think about theory in decision-making. For example, lotteries, choice between lotteries, the difference between the expected values might be a reasonable feature. And then we say, well, maybe use insight features, behavioral insights into the machine learning. We call these the psychological features, and all these features that we tried were based on a specific behavioral model that that is called BEAST and was published in Psych Review 2017. Let me briefly discuss BEAST. BEAST was the baseline model for CPC 15. It's short for Best Estimated Sampling Tools. It assumes basically 5 things. One, sensitivity to the difference, to the best estimate of the difference between the expected values, and 4 additional behavioral tendencies: a tendency to treat all outcomes as equally likely, a tendency to maximize probability of winning. So I don't care about how much, but whether I win or lose, a tendency to assume the worst, be pessimistic, and a tendency to prefer the option that minimizes the probability of immediate regret. And importantly, BEAST assumes that this tendency, the last one, preferring the option of minimizing probability of immediate regret, increases with feedback over the other tendencies. Okay, so this is BEAST. I'm not going to go into more detail than that, but it is a very, very useful model in this case. And I know this because the best models in the competition were actually minor modifications of Beast. The winner was a minor modification of Beast, and many of the other best models were also modifications of Beast. So we took Beast and we decomposed it to its behavioral assumptions and made behavioral features out of them. For example, if I said that one of the assumptions of Beast is that people are sensitive to the worst outcomes, they tend to be pessimistic, then in order to make it into a feature, we let the machine learning get the difference between the minimal possible outcomes in each of the two gambles. So if I assume the worst, what I care about is the minimal outcome here, the minimal outcome here. Their difference is what the machine learning should look at. And another example, minimization of regret. So if people are sensitive to the probability of regret, we computed the probability of regret from A, we computed the probability of regret from B, and we let the machine learning know the difference between these two probabilities of regret. So basically, all our features are algebraic functions of the raw features, of these raw features of the objective features, but we let the machine, we do a lot of the computations for the machine learning algorithms in advance. In addition, we also checked what happens when we let the machine learning model get a feature called the foresight, which is basically the prediction of Beast itself, the prediction of the baseline model, the quantitative prediction that says this is how all these tendencies are merged together. And what we check is different types of algorithms, for example, random forest and neural networks and SVM and whatnot. And these are the results. I'm not gonna discuss much of this, just note that higher is better here. This is the competition winner. This is the level of random guessing. And objective features, using objective features is basically, only objective features is basically almost random guessing. So machine learning without theory did very, very poorly. Moreover, machine learning with just behavioral insights was able to slightly outperform the winner of the competition. And the best one that we got, the best result that we got was using a hybrid model that uses both insights and foresights. So to summarize, in the follow-up analysis, we got, again, very poor prediction for machine learning without theory. We got slightly better than the winner for a hybrid model with only insights, and a new winner of the competition that we call psychological forest when we integrated insights and foresights within machine learning. All right. Now we go on to CPC 18, which is the second competition. And there we had two baseline models. This is a very similar paradigm with more training data, a bit more complex, but not much. Baseline models were two, again, Beast, the same one from CPC 15 with a minor modification, and psychological forest, which is the hybrid model that uses both insights and foresights. We had 46 registered teams to this competition, and from all over the world, 16 countries, 34 institutions, many researchers. And we did a survey asking people, did you invest effort in trying to submit a model to the competition? And they said, yes, very much. The mean time of hours of work was 66. We got 20 submissions. And the winner of this competition is a model that we call now Beast GB, for Beast Gradient Boosting. Why? Because Beast GB is basically the same hybrid model that was the baseline for the competition with insights and foresights using Beast insights and the prediction of Beast as a feature, but replacing the random forest algorithm that we used with a different algorithm that is called extreme gradient boosting. And extreme gradient boosting is a very, very good algorithm that very often wins in many machine learning competitions with similar types of data. So this is not a surprise. This is not a very big result. I didn't know it at the time, but this is a very common result. The extreme gradient boosting is a very, very effective algorithm for combining features. and all the power of the model is down to the features that are derived from Beast. These people are the winners of the competition. They are the one who submitted Beast GB to the competition and won. All right. Now, what we did is we tried to analyze the importance of the different features of Beast GB in predicting the results of CPC18. What you see here, and let me guide you through this, is what you call a SHAP value, which is the SHAP, which is basically the impact of each unique feature on the output of the model. This is on the x-axis. On the y-axis, you have all the different features that were used by Beast GB in the competition, and they are sorted from the most important feature at the top here to the least important feature on average across all observations. What you see here, each tiny point here is basically one prediction problem, prediction problem in the competition. And the color of the points is the value of the feature for this prediction problem. So purple is high, yellow is low. So if we look at the most important feature here, you can see it's called Beast spread, which is basically the foresight model, the foresight feature. This is the prediction of Beast. This is the most important model, and this is a quantification of how important it is. It's much, 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 much more important than all others. Okay, and second, what you see here is that when the feature's value, the Beast prediction value, is low, it's yellow, the output of the model is also relatively low. And when the feature value has when Beast spread has a high value, so it's purple, the output of the model is also very high. Basically saying there is a very strong correlation between the predictions of Beast and the prediction of Beast GB. And every time you see points arranged such that they are from yellow to purple, this means very strong positive correlation. If it's the other way around, very strong negative correlation, and so on. Okay, so the point to take from this, Beast prediction was by far the most important feature, and we can see that it has very high correlation with the actual predictions of the machine learning model. Okay, let's summarize the results of CPC18. We didn't get any submissions that.
You don't have a question, right?
Can you explain what was the parameter of Beast that you use in this was used in this analysis?
So as I said, this is fitted. So usually the foresight is fitted to the training data. So we took Beast as it was fitted to the training data, and we used it as used its prediction.
Okay, thanks.
So it's not refitting or over any sorts. Okay. So CPC18, we didn't get any submissions of these two categories. No submissions that didn't use any machine learning. No submissions that didn't use any foresight features. The winner, of course, was Beast GB, which is a foresight model. And we also had very good models that did not use any machine learning. Now, I'll get to this point in a second, but now there comes the question, why didn't we get any submissions of these two categories? What's happening? So we can ask first for this one, for this category. Are foresight features really necessary for a prediction, at least for CPC18? So what we did is we took the two hybrid models that use foresights, the two best hybrid models that use foresights, which is psychological force and Beast gradient boosting, and we just removed this feature from the model. And what you can see here, I'm sorry for the confusion here, lower is better. This is the mean squared error, lower is better. And here you can see for Beast GB, this is the winner of the competition, right? When we remove the foresight model, its performance greatly deteriorates. Basically, it doubles the error rate. Same thing happens for psychological force for a different algorithm. So I don't know if foresight features are necessary, but at least for these data, without the foresight feature, for these models, it was very important to integrate. Second, are behavioral theories necessary? So we have the additional category. Again, we can't be sure, but again, no submission was made that did not use any behavioral theories, despite the fact that we have 16 different researchers whose main research area is artificial intelligence. So they do artificial intelligence, they know data science, they know algorithms, but still we didn't get any submissions that did not use any behavioral theories. And in fact, the winners themselves are a bunch of data scientists, a very nice group, and they say that we tried a massive hyperparameter NLP, which is basically neural network, for weeks with objective non-behavioral features and data, but performance was strictly inferior to baselines. And I remind you, the baselines were models that used behavioral theories. Now, how can that be? How can that be that, again, we get the behavioral theories are necessary, at least for the choice prediction competitions? And I'll try to answer that in a second. Okay, so one possible answer is that data are too small, but and I'll show you that I don't think that that's the case. But before that, let me summarize. So we get here in CPC 18 in a follow-up analysis, very poor predictions for no theory and for theory without foresights. Okay, so is it because the data is too small? So remember, we have 270 different choice problems, or for the training data, we had 210 choice problems, which is much more than we can usually run in policy types problems. But still, it's very, very little data when it comes to machine learning. So 210 different treatments, too little data. Maybe that's the case. So we had a new data set. It's not ours. So some of the winners of the competition, they ran a new experiment. And in this experiment, they published the results of the experiment and a few other insights that in this paper, science paper, which I recommend, again, reading. It's very interesting and insightful. But the point here is that in order to run this experiment, they had a huge data set. This huge data set used a similar paradigm to the choice prediction problem, choice prediction competitions that I've shown you before. Again, choice between two options, fully described, for example, 16 with certainty and all these for B, and with feedback. In this trial, you chose B and gained 50. Had you chosen differently, you would have gained 16. With some modifications from the CPC data, and for different populations, instead of students, it was M-Turkers, and instead of 25 trials, there were only 5 trials. So there were some modifications, but basically it's a very similar paradigm. And the important point is that there was 9,831 different choice problems in this data set. So we had 210, or 270, they had nearly 10,000. What you can see here on the right is basically each point represents one choice problem in a 2-dimensional space. This is some sort of embedding showing a representation of one problem into a 2-dimensional space. The black dots are their problems. The red dots are the CPC problems. And the X's, the green X's, are the Kalman-Tversky problems from prospect theory and other experiments. What you can see basically is that they have a space that covers a lot more than of the space than we usually cover in our tasks. So it's very nice that we can use this type of data set to test our model. This is from their paper. This is just a print screen from their paper. This shows results of different kinds of models that they've tested in their data set. What you can see here, the way to read this is as follows. What they do is they take the 10,000 problems, the 9,800 and so problems, they divide it to 10% test and 90% train. So the 10% they put aside, they don't look at it. Then they take the 90% and they ask how much of that 90% of these 9,000 problems can we train each of our models on. So 100% is a model that was trained on 9,000 problems, and 10% is a model trained on about 900 problems. So still a lot more than the previous largest data set, which is the CPC data set. What you can see here is the test set mean squared error, and you can see it goes down for many of the models. And what are these models? For example, the yellow one, they call neural CPT, which is basically cumulative prospect theory, where the parameters are optimized using neural networks. So this is basically the best possible version of cumulative prospect theory. And the red one is the best possible version of prospect theory. And the best models that they could find is the purple one, which is context dependent, basically a neural network that learns the structure from the data. What we did is we took their data set and we took their models and we compared it to BeastGB, to our hybrid model. What you can see here is this context dependent, this winner of their model comparison, how it does. And for comparison, the neural CPT, for comparison, Beast, untrained. And this is the line for BeastGB. This is, so by far a win for BeastGB over the best neural networks not having access to behavioral logic, which is the purple one. So neural networks without behavioral theories, this is the best that they could do. BeastGB, a hybrid model that uses behavioral logic from Beast, already from 1% training data, outperforms many of the all other models, and of course it's superior even when neural networks get 9,000 choice problems to train on.
Ori, maybe I missed something, but aren't there some of the authors there the one that submitted the BeastGB?
Yes.
So why and they didn't include it?
No.
Wow. Okay.
Their point was different, but yeah.
Thanks.
Notice that I have two lines here. The one up above is BeastGB, but without the foresight feature, without the prediction of Beast. So before I told you that we must have the foresight in order to predict well in CPC 18. But once we start having much more data, for example, already when we have around 900 problems, it doesn't matter if BeastGB get access to the prediction of Beast or not. Basically, it learns to integrate all the different tendencies assumed by Beast from the data itself. So basically, what we have here is once we have small data, we do need a foresight. Once we start getting more and more data, what we need is basically only the behavioral insights, and the machine learning can learn to integrate them together. But still, the joint impact of behavioral insights and machine learning outperforms any purely machine learning model. Here's again the plot for Shapley values, which is again feature importance for their data, for the 10,000 problems. And what you can see here is again that the most important feature, again by a wide margin, is the prediction of Beast. Again, you can see a very nice, positive, strong correlation between the prediction of Beast and the prediction of BeastGB, which is nice because, for example, Beast is interpretable, while BeastGB is not very much at least. So we can say, well, the predictions of Beast are correlated with the prediction of BeastGB, so we can basically maybe explain to policymakers, for example, or to users of the system, what makes the model behaves as it does. You can explain the process underlying the model to some extent by using Beast. Now here you can see that other features are also very important. For example, the difference between the expected value, this is the difference between two expected values, is an important feature in predicting how people choose between lotteries. Here you have the probability of regret, basically, the difference between probabilities of regret, again, important, and so on, and several non-important features. Okay. So let me go back to this summary table and say, well, wait. Without any machine learning, there is a model that does not statistically worse than the winner. Maybe we don't need machine learning at all. So maybe we don't. So we checked. And luckily, there's a nice analysis. Again, I recommend reading the paper, insightful and so on, by Hay et al., a management science paper from 2022, I think, called The Wisdom of Model Crowds. What they did in this paper, they conduct a large-scale comparison of 58 prominent models of risky choice using 19 existing behavioral data sets involving 800 participants. So again, we have a large data set. And we have a large data set in which we know how purely behavioral models do. What are the best behavioral models? And we can test BeastGB and Beast in comparison on this data set. By the way, these authors did not use Beast in their comparison because excluded models that did not have analytically specified likelihood functions. Okay, and Beast is a simulation model that does not have a likelihood function. Okay, Yafim, when should I finish, given that we started 10 minutes late? How much can I?
Tough question. You promised not to ask me tough questions during the seminar, but I think in about 5 minutes.
Okay, I'll finish the 5 minutes. So I'll just mention briefly that Hay et al. In their analysis fitted all 58 models to individuals. So for each individual, they basically built a different prediction model. BeastGB is a model for predicting the aggregate. BeastGB did not get access to the individual training data. Did not get access to individual training data. We compare it, the results you're going to see, we compare it to an aggregation of all the models that did get access to individual data. So they are at an inherent advantage over BeastGB. A minor point, some of the data sets in the original paper were corrupted. They didn't notice it. So basically, we reanalyze all their work using the right data sets. We have over 1,500 different choice tasks in total here, and we let BeastGB predict here. What you can see here is a comparison of the 58 models with Beast and with BeastGB. Now, when I say with Beast, that's a small lie, because here Beast was not fitted to each individual, and actually was not fitted at all. Its parameters were not fitted at all to the new training data, because it's very hard to fit the model without an analytically derived likelihood function. And this is the performance. Lower is better here. Very, very poor. So the prediction of Beast is very, very poor when it's not, at least when it's not fitted, and at least to this new data set. Here you get BeastGB using as a feature these very, very poor predictions. This is one of the features. And then it outperforms all the other models in the comparison. And just to zoom in, you can see that the difference is not that small, but CPT with a specific function of Plonsky et al. Comes close, although it is fitted to individuals. Again, feature importance. And again, and this is nice, despite the fact that predictions of Beast were very poor for these data sets, the feature Beast's prediction was the most important one in this data set again. Why? Because Beast is in very high correlation, rank order correlation, its predictions and the actual data. The problem is that it has a very large bias. that it cannot capture many of the idiosyncratic effects that we see in this data set. For example, in one of the choice problems in that large data set, people were asked to choose between 100 with certainty and 500 probability 0.9. I mean, I would say that no one in his right mind would choose here S. Still, 50% is the choice rate of R here. I think this is heavily contextual data, so there's something very weird going on, this idiosyncrasy going on in this specific experiment. And Beast, of course, cannot account for that, especially with the original parameters. But then we take its prediction, we integrate it into Beast GB as a feature in a machine learning model, and it corrects for the prediction very, very nicely to outperform all other models. This is, yeah, so I'm saying this is idiosyncrasies because this is actually from a paper that this is what it does. It tries to show that it's very easy to affect behavior of people using different contexts. Okay, now I'll summarize. So we have BeastGB, a new model, Beast gradient boosting, that gives state-of-the-art level predictions of human choice under risk, under uncertainty, in 3 large data sets, diverse data sets with over 11,000 choice tasks, probably the largest comparison ever made. Behavioral features were found to be necessary even when we have 9,000 data problems to train on. However, it seems that the machine learning can learn to integrate the different insights together once we have a lot of data. And finally, machine learning seems to be especially necessary when there are idiosyncrasies, contextual effects that emerge from specific cases, and then we can take the behavioral model and correct for it. That's it. Thank you. Thanks for listening, and thanks for staying with me.
Thank you, Ori. This was very interesting. So now we have just a few minutes for questions because due to my mistake, we started late. So we have a few minutes for questions, and then those who have to go can go, and we will stay for about 20 more minutes to ask additional questions. Yes, Kinela, go ahead.
Ori, I have a question. In your diagram with the purple and yellow, so you have the features and the Beast prediction, it seems to include many features within. So the fact that this is explained the most, maybe it's not that surprising in the sense that it includes many of the other features. No, I'm asking. I'm not sure that.
So, of course, the machine learning, you're right in a high level that the Beast prediction includes all these insights within it. How? It integrates them in a simulation offsite, offline, in some way, and it says this is the explicit way in which all these insights merge together. I could integrate them in a weird manner, in a different weird manner, and my bet is that then such a random feature will not perform well. So it's not the fact that it includes the features; it includes the features in a smart way, and this is the point, right? If you have a good model that knows how to integrate all these insights together, then it will be an important feature.
Moran,
I think we have a question from 20 minutes ago in the chat, so maybe I should answer
you
that.
answered it, if I'm correct.
Ido asked you in the middle, so that's.
Yeah, we don't hear you.
So it was, I think, after I said it, but let me just clarify. How are the parameters set for the Beast prediction feature in the new data sets? In the new data sets, I am not refitting Beast. I'm using the original values of the parameters of Beast fitted for the choice prediction competition 2015 to create the values of the feature of the foresight feature. So I'm not refitting anything. That's just one. Yeah.
Moran.
Okay. Do you hear me?
Yes.
Ani, hi, yeah.
Hi, hello. Thank you, Ori. Great talk. Very interesting. So I have a question. Maybe it's very, very general. So now if I think about the theoretician as a machine, and I'm trying to explain why theory is important or useful, then just, two very naive ideas that come in mind is that the theoretician is trained on larger data sets, but not only, I don't only mean that you increase the N, but as humans, we see people making choices in different contexts. So not only binary choices, ternary choices, or choices from totally other domains. And of course, as theoreticians, we don't only see choices people make, but we actually have, we have language. We can ask them, why did you make the choice that you made? How do you feel about it? And how confident are you in other things? And that informs our theory. So, especially given the new surge of these language-based machine learning models, I guess you could push the point and ask, what if I gave, these machine learning approaches only data, also data about, language data about how people feel about their choice or how they explain their choice. You could easily imagine that this will, make their theory totally redundant. So I guess like philosophical question, but what do you think about that?
Yeah, so I think, it depends on your prediction task, right? So if you think of a specific context, and then you collect training data for a specific context, then maybe you can do an experiment and then ask people and integrate that as well into your prediction model. And I agree, it should help. And there are models like this, for example, for prediction of stock market. There are models that show improvements of predictions when we integrate Twitter data. So we don't ask people, we just mine the data from Twitter or whatever.
Yeah.
So, and language models and so on, and they can be used so we can analyze texts as well to improve predictions in a specific context. And I completely agree. So once you set a context, you can think of different sources of information that you can integrate, and then a large advantage, I guess, that could happen, that could be of machine learning models of this sort, is that they are able to integrate features from different sources, often in a very efficient way. So I agree. That's a very good point. Yeah, thanks.
Thank you.
The last question for today's first part is from Robin.
Well, thank you very much for your presentation. Very, very interesting. I was wondering, you talked about the idiosyncrasies of the big data set. And I think that could have something to do with, I guess, people having to do a lot of choices in that data set. So I was wondering, did that data contain the information, which choice, or the first, the 20th, or the 100th, that was by the particular participant? And the second question is, would it make sense to include something like that? Because I could imagine if making a lot of choices, that people's choice processes change over time. And for example, that example that you quoted, that people just are not that invested anymore in their 50th choice as they are in their first one. Thank you.
Okay, thanks. So the large data set, the 10,000 problem one, it's not that people actually, each person chose, of course, 10,000 in 10,000 different problems. I think there was like 30 or 40 each participant made different problems. And that's the same for the CPC data. In our data, each participant made choices in 30 different problems. And for the CPC data, it's definitely available. And it's and we have analyzed to some extent this point of order effects of how people choose initially versus towards the end. And I'll say a word about that. For the 10,000 data set, unfortunately, the individual level data was not published yet. I was promised that it will be published last year. It was not. So I don't know. So we don't have that data. I assume that it will be published at some point, and then we can look at it as well. For the CPC data, as I said, we do have it. We did analyze it, and to some extent. And if I remember correctly, what we see there is actually not much of an effect of whether people choose, whether it's the first choice problem people make or the last one. Ido, correct me if I'm wrong. Do you remember? You're muted.
No, you're on mute.
You're muted. Ido, you're muted.
Probably he's not only muted, but also on silence.
Yeah. I think Doron wrote a paper. We have a paper with Doron, and I think that basically people are just less confused later on. Initially, there's more confusion, more violation of dominance.
All right. Yeah.
Okay, guys, thank you so much. This was very interesting. Again, I remind those who want to stay and chat with us a bit longer can stay, and those who have to go can go now. I'm really sorry about the confusion with the links.
I forgive you.
Huh?
I forgive you.
Thank you, and see you next time.
Thanks everyone for listening.
Bye.
Are you saying bye or?
No, not to you.
Okay.
I made this mistake last time. I'm trying not to repeat the mistakes one time after the.
You will have to invite Tori again. You owe him a talk.
Yeah,
A 10-minute talk.
I stopped the recording.
Well, yeah, but it was yeah.
I think
You know, I was happy to see that Cohen's base was not doing so bad, considering that it was